we can start. Our speaker is Marco Cantarini from Perugia, who will talk about Elliott-Halberstam. Please.
First of all, I would like to thank the organizers to give me the opportunity to present my work. And today I will talk about averages of the diagonal Elliott-Halberstam problem, twisted by the Mobius function with Sobolev and all the Zygmunt weights. The starting motivation comes from additive problems involving primes, especially the Goldbach conjecture. More precisely, I will discuss a suitable variant of the very well-known Elliott-Halberstam conjecture that I call diagonal twisted Elliott-Halberstam conjecture, strictly connected to the Goldbach problem and inspired by a work of Wang and Li. And we will prove some non-trivial estimates for a weighted average of such conjecture, assuming reasonable hypotheses and taking suitable weights. So let me first outline the structure of this talk. It's very well known that variants of the very famous Elliott-Halberstam conjecture play a central role in many open problems in number theory, for example, small gaps between primes or the twine prime conjecture. And this is still true also for the binary Goldbach conjecture. So the talk follows 6 steps. The first step is the motivation, why we decided to consider this problem. So I will recall the Goldbach conjecture, the main difficulties that we know to prove such conjecture, and a suitable variant of the Elliott-Halberstam conjecture introduced by Wang and Li that in some sense, if proved, allows to overcome such difficulties and allows to prove the Goldbach conjecture. Next, we will see a different, in some sense, weaker version of Wang and Li formulation that I call the diagonal twisted Elliott-Halberstam conjecture. And this new variant has some advantages with respect to the Wang and Li formulation. For example, it admits suitable formulation in terms of sums involving Dirichlet characters, and it is quite useful for our aims. And even if it is in some sense a weaker version with respect to Wang and Li formulation, it is strong enough to continue to imply the Goldbach conjecture. So it is an interesting variant of the Elliott-Halberstam conjecture to study. Next, we will see the main tools of this work, that is two-dimensional Abel summation formulas, a continuous version and a discrete version. And we will see that using these tools, we are able to prove non-trivial estimate. So for some weighted average versions of the diagonal twisted conjecture, assuming reasonable hypotheses and taking suitable weights. Essentially, we will work with weights that belong or to the Sobolev space W21 or to the older Zygmunt space C delta for suitable deltas. Lastly, we will see a logarithmic weighted case of the diagonal twisted conjecture, and essentially we will prove the same results. Note that the logarithmic weighted case is not just aesthetic, because as we will see in the next slides, in order to prove the Goldbach conjecture, both these variants, the non-logarithmic case and the logarithmic case of the diagonal twisted conjecture, must be true. And so the logarithmic case is an interesting and important version to study. Okay, the Goldbach problem is a very, very famous conjecture which states that every even number greater than 2 is the sum of 2 primes. A standard way to encode this conjecture, also even if in a weighted form, is to study the function Rn, which is essentially a discrete convolution of the von Mangold function. And morally, the positivity of this function is equivalent more or less to the Goldbach conjecture. It's commonly believed that today the main great obstacle to prove this conjecture is the so-called parity barrier. Roughly speaking, the parity barrier says that the main techniques that we know to attack this problem, in particular the sieve methods, are unable to distinguish effectively between integers with an even number of prime factors and integers with an odd prime factors. And this distinction is crucial for such type of problems. So it is quite natural to try to insert some information in some way to overcome these difficulties. And this is essentially what Wang and Li did, following an approach of Murthy-Vatwani for the twin prime conjecture. And so they proposed a suitable variant of the Elliott-Halberstam conjecture that they called twisted Elliott-Halberstam conjecture. Essentially, they replaced the summatory function, the von Mangold function, with essentially discrete convolution between the lambda function and the Mobius function. And clearly, the presence of the Mobius function in this form, using these conjectures, allows to insert some information that, in some sense, overcomes the difficulties, the parity barrier. Indeed, the authors proved that if this conjecture is true for some theta from 0 to 1, and the classical Elliott-Halberstam conjecture is true for 1 minus theta, then the Goldbach conjecture follows. This means that by the Bombieri-Vinogradov theorem, that if one proves this conjecture for some theta greater than 1/2, then the Goldbach conjecture follows. Note that in this formulation we have two maximum, and actually the maximum over A and Q can be avoided. It's not important, and the maximum over Y is present just for a technical reason. Indeed, the authors proved that if this conjecture is true, another variance of this conjecture is true. Essentially, if you replaced in this conjecture the Mobius function with the Mobius function and the logarithmic function. And both of these variants must be true in order to prove the Goldbach conjecture. So with one formulation, they use essentially two variants of suitable variants of the Elliott-Halberstam conjecture. The problem for our aims or our techniques is that this version is not very useful. In particular, we have the main issue is that in the summation we have the parameter y, and as argument to the Mobius function we have n. So in some sense we lose the symmetry between these two numbers, and this is quite annoying for our aims and our techniques. So the idea is to propose a different version of the Wang-Li conjecture that we call diagonal twisted Elliott-Halberstam conjecture. Essentially, we removed the two maximum here, so in this sense is a weaker version of Wang-Li conjecture, and this way we restore in some sense n in the summation and n as an argument. And on the other hand, since we removed the maximum, we lose the symmetry, the implication between the non-logarithmic case and the non-logarithmic case and the logarithmic case. So these two cases must be treated separately, and this is the reason why we decided to define this conjecture in this way. So the conjecture must be true if G is the Mobius function and where G is the Mobius function and the logarithmic function. Even if this conjecture, as I said, is weaker in some sense with respect to the Wang-Li formulation, it is strong enough to continue to imply the Goldbach conjecture. Indeed, we have this theorem that essentially follows the proof of Wang-Li. And so if we have the Elliott-Halberstam conjecture in this form for some theta, and we have that the diagonal twisted Elliott-Halberstam conjecture also for 1 minus theta, then essentially the Goldbach conjecture follows. So this new variant of the Elliott-Halberstam conjecture maintains in some sense the connection between the connection with the Goldbach conjecture, so it is an interesting variant to study. Another advantage of this formulation is that if we take the main difference, note that in this case we are working with the non-logarithmic case, but we can do the same reason also in the logarithmic case. We take the main difference, we can write essentially using the orthogonality of the Dirichlet characters, this difference as this sum, essentially a discrete convolution involving the Dirichlet characters with a small error term. And so we decided to study a weighted average version of this object that is the function AQ, Fn, where f is a sufficiently regular function where its support is contained in alpha beta contained in the non-negative real numbers. Note that the weight f in this form restores the symmetry between the prime variable and the Mobius variable, turns the problem into an additive convolution, and as we will see in the next slides, allows in some sense to uncouple the contribution, the von Mangold function, and the contribution of the Mobius function. Okay, as I said, we work with suitable weights. Essentially, we will take weights that belong or to the Sobolev space W21 or to the older Zygmunt space C delta, where delta runs from 1 to 2. Why this choice? This choice is connected to the main tools. We will see that essentially we will need to, if f is sufficiently regular, we will need to evaluate, to estimate in some sense an integral involving the second derivative on the weight. And this is the reason why we take this particular Sobolev space. And f is less regular with respect to the previous case. We will need to evaluate a second order forward difference of f. And you can find the definition in the last line of this slide. So in order to control this object, we will need to take f in this functional space. So essentially, this choice is connected to the main technique. Okay, in this slide, I just recall the definition for ordered Zygmunt space. I just mentioned that if delta is an integer, actually the ordered Zygmunt spaces are equivalent to the Zygmunt spaces. Okay, the first tool, a continuous version of a two-dimensional Abel submission formula. And actually, we proved this formula in a more general setting, but I decided to consider this version because in the general setting, we have some additional terms that strictly depend on the behavior of the arithmetical function and weighted boundary, and it is a bit messy. And so I decided to take this form because the important information in some sense is encoded in this formulation, in my opinion. This formula, which states essentially that a weighted average of two arithmetical functions g2 and g1 can be written in terms of these double integrals. And note that we have here, as I said, the second derivative of the weight. So it should be clear now the idea why we will work with Sobolev space. And we have here a convolution involving the summatory function of g2 and g1. So in our case, we will need to work with the psi function x key and the Mertens function mx. The second tool is a discrete version of the two-dimensional Abel summation formula. So we have that if f is less regular with respect to the previous case, we are still able to write the weighted average of two arithmetical functions in terms of, in this case, a discrete convolution between the summatory function g2 and g1, and the second derivative is replaced by a second order forward difference. And again, it should be clear now why they decided to work with all the Zygmunt space, because in this, if f belongs to this particular functional space, we are able to control in some sense this object. Okay, in both cases, we have that the main average can be written in terms of the summatory function psi and m. So the idea now is to insert the truncated explicit formula, the first one at level t and the second at level u, of psi and m. And to doing this passage, we need some assumption. The first assumption is the generalized Riemann hypothesis. Actually, this hypothesis is in some sense natural for this kind of problems, and we want to use this technique clearly, because from the proof is quite evident that if we have just one non-trivial zero of one Dirichlet function far in some sense from the critical line, this fact implies a weaker estimates for the weighted average. So in order to maintain the estimate for the weighted average non-trivial, we have to assume the generalized Riemann hypothesis. The second assumption is connected to the fact that clearly if you want to work with the explicit formula of the Mertens function, we have to say something about the simplicity of the non-trivial zeros of the Riemann zeta function. And actually, we need a bit more. We need to control some suitable discrete moments involving the first derivative of the Riemann zeta function. And this control is well encoded by the well-known Gonek-Ejar conjecture that claims that the moments jk are controlled by this function, not as these symbols mean upper bounded and lower bounded by. Clearly, this conjecture implies that all non-trivial zeros of the Riemann zeta function are simple, and actually is too strong for our aims. We just need that the first moment J1 is upper bounded by t, and note that the function t is perfectly compatible with the conjecture. We will call this relation weak Gonic-Kejar conjecture. Okay, we are able to present our main results. So if we assume the generalized Riemann hypothesis and weak Gonic-Kejar conjecture, we are able to prove that if f belongs to the Sobolev space W21, essentially the main average admits these upper bounds. Not that this bound in N is perfectly compatible with the conjecture, and better, we have here power saving. It has explicit in terms of the second derivative of the weight, and moreover, it holds for essentially the optimal range of theta, because we have here morally that theta is minor than 1, which is the best possible choice for theta. Okay, the proof strategy should be clear now. We apply the two continuous two-dimensional Abel summation to the main average. This allows to rewrite the average in terms of the psi function and the Mertens function. So we insert the explicit formulas of psi and m. In this way, we are able to exchange the integrals with the sums, and the integrals can be evaluated in terms of a suitable combination for the Euler gamma function. So the problem boils down to obtain a good estimate to sums that runs over non-trivial zeros of the Riemann zeta function and over non-trivial zeros of the Dirichlet L function involving suitable combination of Euler gamma function. And this can be done using several techniques and using the hypothesis, so the generalized Riemann hypothesis and the weak Gonic-Kejar conjecture. And then we choose the truncation error suitably. So we take t essentially equal to u essentially equal to n, and finally summing over q, we obtain the wanted estimate. Then we have our second main results. So if we assume the generalized Riemann hypothesis and the weak Gonic-Kejar conjecture, then if f belongs to the older Zygmunt weights, where delta runs from 1 and 2, we have a similar upper bound. Note that in this case we are unable to, the implicit constant depends only, or also depends on f. And moreover, the level of theta is strictly connected to the regularity of the weight, because if delta runs from 3 over 2 and 2, we have the first results. And note that if delta is near to 2, we have essentially the best possible level for theta. And if delta runs from 1 and 3 over 2, we have this uniform upper bound. This happens because in the second case, in order to obtain a non-trivial estimate for the weighted average, we need to change the proof, change the main strategies. But it is interesting to observe that the level of theta does not fall below the 1/2 threshold. The main strategy, the main ideas of this theorem are similar to the previous one. Clearly, we have, since we are working in a discrete case, we need to change several techniques, but the main idea is very similar to the previous one. Okay, as I said, if the main goal is to prove the Goldbach conjecture, as we said, the non-logarithmic case and the logarithmic case are both important in order to prove the Goldbach conjecture. So essentially, we made the same type of study for the logarithmic case of the diagonal twisted conjecture, and we get essentially the same results. So if assuming with the same assumption, we obtain that if f belongs to the Sobolev space W21, we obtain a non-trivial estimate for essentially the optimal level for theta. And if f belongs to the older Zygmunt space, we obtain a non-trivial estimate for a level of theta strictly connected to the regularity of the weight. So let me give two examples of admissible weights. The first one is the very well-known Cesario-Ritz weights, very used in number theory. Essentially, if k is greater than 1, it's possible to prove that this function falls in the Sobolev framework. And so the first main results tell us that the Cesario average of the diagonal twisted conjecture admits a non-trivial estimate for a level of theta which is essentially the best possible, that is 1. The second case is a Zygmund type weight, so it is possible to prove that this function is not belongs to the all the Zygmund space, but it belongs to the, in this case, Zygmund space C1. And so a weighted average version with this weight of the diagonal twisted conjecture means a non-trivial estimates for a level of theta which is essentially 1/2. So let me summarize the main conclusion. So we proved that non-trivial estimate for a suitable weighted average version of suitable Elliott-Halberstam conjecture strictly connected to the Goldbach problem. And we introduce a method that in some sense uncouples the contribution of the von Wangold function and the Mobius function, and allows to rewrite the main average in terms of explicit formulas of the psi function and the Mertens function. And so, assuming reasonable hypotheses, we are able to obtain non-trivial estimates for such average for a level of theta which is strictly connected to the regularity of the weights involved. Okay, let me finish with some open question. The first question is, how essential is the dependence on the weak Gonick-Kejal hypothesis? So we use this hypothesis, as I said, to control suitable discrete moments involving the first derivative of the Riemann zeta function. But it will be interesting to understand how essential this hypothesis actually is and if can be weakened in some way. The second question is, can weight regularity be replaced by a more arithmetic input? As I said, if we want to use this technique, we need to assume some suitable hypotheses on the weights, but one may ask whether sharper arithmetic estimate could be compensated in some sense weaker, less regular weights. Lastly, what change should be made to the technique to address the study of a non-weighted average version of the conjecture? Again, if we want to use these techniques, we need to take suitable weights, sufficiently regular weights, but it would be interesting to study a non-weighted average version of this conjecture, and this is what we have been doing very recently with a new work that has just been submitted, so we hope to obtain. So we think we will obtain a non-trivial result in this direction. Okay, just we have here just selected reference. I would just like to point out that the result of Wang-Li, which I frequently cited during this talk, was presented at this very conference about 6 years ago. Okay, thank you.
Thank you very much. Are there any questions for our speaker? Oh, if not, we thank you again.
Thank
And
you.
the next talk will be in 7 or 8 minutes. So Aviral, if you want to share the screen with your slides.
Yeah, hi Melvin.
Hi.
I'm just presenting my slides. Just a minute.
No rush. Plenty of time.
Are they visible to you?
Yes. Oh, there it is. That's very good. You might want to make it full screen if you can.
Is it fine now?
No, that's perfect right now. Good.
Okay.
Okay, we'll wait 5 minutes.